So this is a tutorial on proofs and the Coq interactive theorem prover, which we're using for this user interface experiment. So Coq is a tool for writing proofs. It's been used for both general mathematics and proofs about software and computer science. And these proofs can be very complex, though we'll just be sticking with some relatively simple ones. Coq works by helping to ensure that your proofs are correct and, of course, complete. So ultimately, we want to know if propositions like the following two must logically be true. So first, if it is raining, then the grass will be green. And second, if it is raining, then it is raining. So we can translate statements like these into symbols and use Coq to reason about them. So, for instance, if P stands for if it is raining and Q stands for the grass will be green, then we can translate if it is raining then the grass will be green and if it is raining then it is raining into P arrow Q and P arrow P, where we're using this arrow operator to just mean implies. Assuming we don't know anything about how the current weather is or how the grass grows, P arrow P must be true, and P arrow Q might not be true. It might be true, it might not be. So what's interesting is that this is still the case even if we set P to program A works correctly, and Q to program B works correctly. And this is assuming still that we've got no knowledge about P or Q, that is, about program A or program B. Of course, we might actually know, or at least want to assume that we know, some facts relating to P and Q. So in general, we call this set of things that we either know or are hypothesizing, we call this our context. So let's assume that P actually does mean program A works correctly, and that Q means program B works correctly. And let's add this new variable R and have it mean that program C works correctly. Our context might contain two propositions, P arrow R, which translates as if program A works correctly and if program A works correctly, then program C works correctly, and R arrow Q, which means if program C works correctly, then program B works correctly. So then what we really want to prove is a formula with a given context. That is, with a set of formulas that we are assuming are true. So in Coq, we might see our context and a formula displayed as something like H colon P arrow R, followed by H0 colon R arrow Q, then a line separating our context from our formula, and then the formula itself. And here we're using H and H0 basically just as labels for our hypothesized proofs of these two formulas in the context. So we generally refer to this whole thing as a goal, although sometimes we also refer to just the bottom formula as the goal as well, unfortunately. So how do we actually create proofs? Well, in Coq, we create them by entering commands called tactics, which either transform goals into new goals, or point out that the current goal is obviously true. So what winds up happening is you end up with a tree of goals where your original goal, which is your theorem or lemma that you're wanting to prove, is the root, and the obvious goals are the leaves. And for historical reasons, we usually display the tree with the root at the bottom and the leaves at the top. So now I'll get into some details within the CoqEdit environment. The first thing to learn about Coq and CoqEdit, or rather CoqEdit, is how to use it, how to use the menu items in the plugin. So it's actually a jEdit plugin. We're using jEdit here, and you go to plugins. You go to CoqEdit, and the two menu items that you really need to learn about are Control-N and Control-P.
forward one sentence and back one sentence, but most of the time you'll want to use the shortcuts. N for next and P for previous. So CoqEdit sends messages to a backend for Coq, called CoqTop, and it does so sentence by sentence, where the sentences are delimited by these periods, followed by white space, and so it's just like in English. And we can move forward a sentence by pressing Ctrl-N, and that moves this highlighting forward. If we do that again, we move it forward still further, again, and actually we've run out of sentences to evaluate, because this guy here, as well as this guy back here, that's all comment. So comments are just written open parenthesis, star, the comment, and then star, close parenthesis. So we can move back and forth within this the evaluated region, and we can move back and forth even if we haven't evaluated the buffer fully. Occasionally, we may find ourselves evaluating an error, and that'll actually prevent us from continuing on. So if we go Ctrl-N again, we get this red highlighting, and if we try going Ctrl-N again, oops, alright, we go Ctrl-N, and then if we try going Ctrl-N again, we aren't able to. I press Ctrl-N, press, and nothing happens. So the way to get around this, you have to fix your mistake, basically. So you can type in here, and that'll get rid of the red highlighting, and we can try to evaluate that nonsense here again. We can also move back the evaluation back by typing within the evaluated region, this green area here, and that'll move us backwards as well. So if I didn't say it already, what you're seeing over here is the result of evaluating the sentence over here that's highlighted in dark green. So the red highlighting is really helpful because if you're actually writing a proof, which we haven't yet attempted to, this will prevent you from making an incorrect proof. Also, sometimes when you save the file, the highlighting will go away. That's a limitation of this interface. But we can just go back and re-highlight things, so it's not a big deal. So let's take a closer look at the sentences that we evaluated already. What we've actually done here is to declare some variables. What we've said is P, Q, R, and S. These are all variables of type prop. So the colon here means means type. And prop stands for proposition. So we're basically saying that P, Q, R, and S, these are propositional variables that we're going to deal with later on when we start to prove things. We actually could have written all these variable declarations in one sentence, and I'll do so now. So we just write parameters P, Q, R, S. These are all of type prop. I'll get rid of this guy and this guy, save, and reevaluate. And over here we see P, Q, R, and S are assumed. Let's try to prove something quite simple. We'll call it simple proof, and we do it by writing lemma, and then simple proof. We're naming our proof, and let's give it a very simple lemma, P implies P. Let's evaluate this. So when we evaluate this, we see over here on the right that we've got a goal. It actually says subgoal, but either way, whatever we call it, it works. So the goal is P implies P, just what we started with. So we play around with these. We try to prove lemmas, playing around with goals, and trying to get rid of these goals. So once we've gotten rid of all of our goals, we've actually proved the lemma as a whole. So we get rid of goals, or change them at least, by entering tactics. So the first tactic that we're going to use is called intro. And when we evaluate this, our goal changes. So now our goal is to prove P, but our context has changed. So we want to prove P in a context where we've got a proof or evidence H of P. So basically what happened was that this P here got moved up into the context. The second tactic that we need to use to prove this lemma is called apply, and we actually use apply H for this hypothesis here. When we evaluate that, we actually don't have any more subgoals. So this really was about as simple as it gets. To save the proof, we just write QED, evaluate that, and we've saved it. We'll try to prove something just a little bit more complicated now. Let's call this new lemma simple proof 2, SP2. And we'll try to prove that P implies Q implies T. And so one thing that you should really understand well is that this arrow operator is right associative, meaning that we have these implicit parentheses right here and right here. But we can leave them off, and actually, when we get our new goal, Coq will leave them off for us. So let's evaluate this. So now we've got this goal here with two arrows. How do we prove this? Well, in a very similar way to how we proved the original, our first lemma, simple proof. We just go intro, evaluate that, intro again, evaluate that, press Ctrl-N, and now we see that we've got two hypotheses in the context, H and H0. And Coq actually automatically labels these. It just keeps numbering H, H0, H1, H2, H3. So for our purposes, you don't really need to worry too much about hypothesis naming. So how do we solve this? Well, we just go apply H again. Evaluate that, no more subgoals, QED. We're done. So an alternative way of doing this, we could save ourselves a little bit of work. Back here, we do the intro. We do intro twice, and we can replace this double use of intro with just another tactic called intros. So that just sticks all the left-hand sides of the arrows up into the context. It repeatedly does intro. So we've saved ourselves a little bit of work there. Let's call the next simple proof that we'll do SP3. And we'll prove that P implies Q implies Q. So just as a reminder, the parenthesization here is like so.
that's just implicit, so we'll leave that off. So let's evaluate that. Alright, and we've got our goal. P implies Q implies Q. So we could do intros. I'll do intro and intro again first, just to make things a little more clear. Get H as a proof of P. Intro again. And H0 as a proof of P implies Q. So let's change these to just intros. Saves us one step. And now, we can't use apply H here because H is a proof of P, it's not a proof of Q. However, we can prove Q if we can prove P. And we can do that because we've got H0. So we can apply H0. And now we need to prove P, so we can use H. So we can apply H. And now we've got no more subgoals, so we're done. I'll now digress briefly and show you a proof using an alternative proof viewer. So here you can see our proof tree. Down at the bottom here is our root goal, and up here are the leaves. And the reason this bottom one is orange is actually just because it's our current goal. So it's just the one that we zoom in on when we zoom in. So I press I to zoom in, O to zoom out, and we can use the arrow keys to move around the proof tree. So going up, over, up further, back down further, zoom in, we can do the same thing, move around like so. And in case you forget what keys to use, these are just printed down here at the bottom. So our initial goal is P implies Q implies R, implies P implies Q, implies P implies R. And this intros tactic just produces this new goal up here. Then we use apply H to produce these two new goals. This one's taken care of completely by the apply H1, and this one's taken care of first by using first apply H0 and then apply H1 on the resulting goal. One of the major features of this visualization is that we can actually play a short animation and add some highlighting to show how the tactic matches various bits of text and to show which bits of text appear down in the parent goal and which appear are new in this child goal here. So by pressing T, you see here we've got matching text, here we've got matching text, here we've got matching text, and here we've got matching text. And this green stuff is new, the red stuff is old. It's deleted in the child goal. So then when we go up to this apply H tactic and we press T again, we see that these H's match, these R's match, the P's match, these Q's match, and then the contexts as a whole both match. So the reason this actually works is because we've got H here as a proof of P implies Q implies R. So we need P to prove that Q implies R, and then once we've got that, we can use Q. So if we've got both P and Q, then we've got R. So a final note, some of the proofs that you'll look at later on get quite large, and it's pretty easy to get confused about whether you've seen a node before or not. Some of the nodes are actually identical, but they appear in different places within the proof tree.
So to help you out with this, you can actually press the key V to mark a node as visited using this purple square, and you can continue on this way and mark nodes as you go along. And in case you want to remove this square, you can just press R. So the next proof that we'll do will be SP4, and it'll be a proof of P and Q. We're using the // sort of up arrow notation to indicate and then implies P. So the way we prove this is we again go intro. No need to do intros, because there's only one arrow. And now we've got a hypothesis H that P and Q are true. And actually, we can just apply this directly. And that'll solve our problem. So this makes sense, right? Because H is a proof of P and Q, which basically means that it's a proof of P and it's a proof of Q. Another way that we could have solved this problem, proven this lemma, is to write destruct H. And that basically gives us two new hypotheses. H and H0, gets rid of the old H and replaces it with this new one. Basically because the only way we could have proved P and Q is to prove P and to prove Q. So the destruct tactic recognizes this fact. And then we can apply H again. So the next lemma we'll try to prove will be SP5, that P implies Q implies P and Q. Evaluate that, as we expect. Then we go intro. Actually, we can do intros here. And we've got H as a proof of P and H0 as a proof of Q. What we now need to do is to prove both P and Q. That's our goal, really. And the way we handle this is we use the tactic split. We evaluate that, and now actually we have two goals. So our first goal is to prove P in this context, and that's actually our current goal, so we'll work on that first. And later on we'll try to prove the second goal. So we can prove P just by using H. So we just go apply H, and that actually does it. So we'll move automatically to the second goal. So now we see this same context with this goal Q. We can use H0 this time. And now we're done. Let's try to prove lemma SP6 that P implies Q implies R. That guy implies that if you have P and Q, then you have R. And for clarity's sake, let's put in some parentheses right here and here. That won't actually make any difference, but I think it makes it easier to read. So I'm going to prove that this guy implies this guy. So let's start. The first thing that we want to do is intros. And now we want to use H, because H is saying that if we have a proof of P, then if we have a proof of Q, then we have a proof of R. So apply H actually gives us two new goals to prove, P and Q. So we'll work on the first one. We can prove P by using H0. So we could use apply H0, or we could use destruct again. Let's use the latter. And that changes our context, as we saw before, to H0 as a proof of P and H1 as a proof of Q. So we just use apply H0, our proof of P, and that gets rid of this goal. Oops. Alright. So now we just have one goal left. And we can do the same thing again. We can destruct H0, and now we use H1. Apply H1. QED. So let's now try to prove the converse of what we were trying to prove with SP6. Let's try to prove that P and Q implying R implies that P implies Q implies R. And let's call the proof SP7. Alright, so the way we do this is very similar. We use intros, which gives us 3 hypotheses for our one subgoal, which is to prove R. And we can use our first hypothesis, H, which says that if we've got a proof of P and Q, then we've got a proof of R. So we apply H. Now we've got to prove P and Q, so we split, which gives us 2 subgoals, both with actually the same context, with these 3 hypotheses. So here, in this first subgoal, we just use H0, our proof of, or our evidence of P. And then for the second subgoal, which we move to automatically, remember, we use apply H1. And now we're done. So suppose we want to prove what we proved with SP6 and what we proved with SP7 just as a single lemma. So what I mean is, suppose we want to prove this and the converse, this guy. Suppose we want to prove that. We'll
call it SP8. Well, it's pretty easy to prove now that we've done SP6 and SP7. All we have to do is do split. And now we've got the two goals that we had lemmas. So we can actually just copy and paste. And we want to do this one second. And this one first. Let's see if I did this right. Now we're done. So that was pretty easy. The reason that I wanted to introduce this, though, is that we've got a special notation for this sort of statement. It's if and only if. So note that, basically, we've got the same thing, but with the arrow reversed. So here, we've got P implies Q implies R, implies P and Q implies R, and here we've got the converse. So P and Q imply R implies that P implies Q implies R. So what we want is if and only if. And generally we use the arrow going both ways, or the double arrow. So we want to use this symbol. And it turns out that in Coq, you can actually just do that. So you can get rid of this arrow and replace it with a double arrow, and get rid of the rest of your lemma that you're trying to prove. And now, we can just go ahead and prove it the way we would have if we had written it out in full. So this double arrow, this implication, double implication, if and only if, is really a handy shortcut. So far, we've looked at how to deal with three operators on these propositional variables. So the first operator is this implication. The second operator is the conjunction, the and. And the third operator is just the if and only if, the both ways implication. So we're going to move on to a fourth operator, which is disjunction, so or. And then we'll have just one more to go through. So here, an example will be, suppose we've got P, then we've got P or Q. Intro again as usual. Alright, so here, from this hypothesis P, we want to prove that either P or Q is true. And the way we do this is we use either left or right. So, we can use left to change this goal into just being P. And now I can just apply H. So if the lemma had been slightly different, if it had been Q or P, that's when we would use right.
we still need to deal with the case where we've got a disjunction, an or, in the hypothesis, as a hypothesis. So let's look at another example. Suppose we've got P or Q, and suppose that P implies R, and Q also implies R, and we want to prove R. Alright, so doing intros again, we've got three hypotheses, and the first one, H, is this disjunction, this or of P or Q. So we know that either P or Q is true, possibly both, and we want to prove R. So we can't prove R directly from either H if we used H0, and we'd have to prove Q if we used H1, and we can only prove that either P or Q is the case. However, if we go destruct H, now we've got two goals, and just looking at our first goal, we see that H has now become just P. And you'll see in a second here that in the second goal, the context is different. So the goals are the same, the end goals are the same, but the contexts here are different. So now we can prove R quite easily. We just go apply H0, and then apply H. And that gets rid of our first subgoal. Now you see that we've got this H as Q, as a proof of Q, I should say. And now we can also prove it in a similar way. We can go apply H1, apply H, and now we're done. So the final operator that we want to discuss is the not operator, negation. So let's try to prove that if we've got P implying Q, then not Q implies not P. So I'm just using the tilde for not. So we can go about doing this, proving this by writing intros as before, and note that this unary operator, this not, is tightly binding. So how do we deal with the not? Well, the tactic that we need to use is called unfold not. And it just transforms this not P in this case, or not Q if it were down here. We would transform that into P implies false. So let's see that. And if we want to do the same thing in the context with H0, we can write unfold not in H0. So basically, not is just defined as whatever it's applied to implies false. But what's false? Well, for our purposes, false is a proposition that can't be proved. It's just like P or Q or R, but it's got a special property which is that its negation is provable. So if we try to prove not false, we can easily do this. Unfold not gives us false implies false, and we can just use intro and apply h. Alright, so the idea is that false should never be provable, and not false should always be provable. So that gives you some intuition as to why not is actually defined this way, as implies false. Back to our example, we've unfolded both of these nots, and we can just prove the lemma in the same way we've been proving lemmas involving implications before. So we write intro, and then we write apply h0 and apply h and apply h1. So there's one trick here that I'm going to point out that we could have introduced a lot earlier. Instead of writing apply h, because our hypothesis h1, this guy, was identical to the end goal, because we had a hypothesis that was identical to this, we could just write assumption instead of apply h1. That's just an alternative. You don't have to use it. A final point, if you want to tell Coq that Coq should just assume that you've proved a particular goal, you can use the admit tactic. So for instance, if I replaced all these tactics with just admit, I could continue on to the next lemma without having actually proved this one. I'll now summarize all of this. To prove a lemma or theorem in Coq, try to get rid of all the goals by evaluating tactics while in proof mode. Entering proof mode happens when a sentence starting with lemma or theorem is evaluated. Leaving proof mode happens when QED is evaluated. Use Ctrl-N to move your current view, shown with dark green highlighting, forward one sentence, which may mean evaluating a new sentence. Use Ctrl-P to move back. Type in the green region or red region if there is an error to undo the evaluation at or after that point. Each goal has its own possibly empty context. Different goals may have different contexts. However, if there are multiple remaining goals, only the current goal, the first goal in the list of goals, actually has its context displayed. A context is a list of hypotheses for a goal. Each hypothesis, that we've seen anyways, is really stating that there is a hypothesized proof of some propositional formula, and we write hypotheses, name of hypotheses, hypothesized proof, colon, formula being proved. We may refer to a hypothesis sometimes by the name of the hypothesized proof and sometimes by the formula being proved. Here is something of a cheat sheet for operators and tactics. So in the following rules, A and B, and A1, A2, A3, etc., represent formulas where a formula could be a propositional variable like P or Q, or it could be a more complex expression like Q implies P, P implies Q implies R, or P and Q and R. Note that Coq uses implicit parenthesization, so for instance, P implies Q implies R is really P implies Q implies R, and P and Q and R is really P and Q and R. In the following rules, we also assume that all implicit parentheses have been made explicit. Implies. So if a goal is of the form A implies B, you can use the tactic intro to change the goal to just B, with A as added as a hypothesis in the new goal's context. The tactic intros just performs intro repeatedly. If in the context of the goal, a hypothesis H is of the form A1 implies A2 implies A3, etc., up to AN implies B, and the goal is B, then apply H will replace the goal with n new goals, A1, A2, up through AN, each with the original context. Note that n may be 0, i.e. H may just be B. In this case, apply H simply removes the goal. Also, if n is 0, the tactic assumption may be used instead of apply H. And if the goal is of the form A and B, the tactic split may be used to replace the goal with two new goals, A and B. Each of these has the same context as the original goal. If a hypothesis H is of the form A and B, the tactic destruct H will replace H with two new hypotheses, A and B. If and only if. If the goal is of the form A if and only if B, the tactic split will replace it with two new goals, A implies B and B implies A. If the hypothesis H is of the form A if and only if B, the tactic destruct H will replace H with two new hypotheses, A implies B and B implies A. Or, if the goal is of the form A or B, the tactic left will replace A or B with just A, while the tactic right will replace A or B with just B. If, in the goal's context, a hypothesis H is of the form A or B, the tactic destruct H will replace the goal with two new goals, where in one goal's context, A or B has been replaced by just A, and in the other goal's context, A or B has been replaced by just B. Finally, not. If a goal contains subformulas of the form not A, the tactic unfold not will recursively replace each subformula with the formula A implies false. If a hypothesis H contains subformulas of the form not A, the tactic unfold not in H will recursively replace each subformula with the formula A implies false. Note that false may be treated the same way one would treat any other propositional variable. So finally, a reminder on how to use the alternative visualization. You can use the I and O keys to zoom in and out. You can use the arrow keys to move around the tree. You can use the T key to play a short animation showing where there is matching text, and to add highlighting to show where there is text in the child goals that does not appear in the parent goal, and where there is text in the parent goal that does not appear in the child goal. You can use the V key to mark nodes that you have visited, and use the R key to remove such marks if you make a mistake. And this information is also presented in the bottom portion of the visualization window.